Let's talk about calorimetry. So calorimetry is this is literally the way they determine how many calories are in food. So right here I have a Cocoa Puff and I'm lighting that on fire. And then as you can see, that can has water in it. And then that water is going to heat up based on how much energy that Cocoa Puff releases. Now, ideally, if I can pause this, all that heat is going to the can and the water to heat that up. But the reality is that heat is radiating in all directions. It's heating up the plate, it's heating up the bar, it's heating up the air around. So the surroundings are all getting heated up. It'd be nice if it was all directed to the can and the water, but the reality of this lab is that there's some places where it can go. But the energy will go mostly into the water in the can, and as a result of that, the temperature will go up for the can and the water. Look at that great camera work. All right, so if we were trying to figure out how much heat was given off by the Cocoa Puff, we would want to know how much heat went into the water in that can and how much heat went into the actual can. So we're going to use the mass of water, the change in temperature of water, and the specific heat of water, and we're going to add it to the mass of the can, the change in temperature of the can, and the specific heat of the can. So notice, because the can and the water are connected and they're in thermal equilibrium, they had the same change in temperature. So the change in temperature for both the can and the water was 4.7 degrees Celsius. Water has a density of 1, so 100 mils is 100 grams because it's 1 gram per mil. And then we just put all that stuff in. So it's 100 grams of water. Change in temperature is 4.7. Specific heat is given on a chart. I would never ask you to remember that. Okay, so specific heat of water, and we're going to add that to the mass of the can, change in temperature of the can, and the specific heat of aluminum, which is also on that chart, which I would give you. So add them up, and that's how much heat was released by the Cocoa Puff. That's where all that heat came from. The reason the water and the can were warmer is because the Cocoa Puff released heat. Okay. Antoine Lavoisier, the same guy who did our balancing equation stuff, he was always curious about this. Does fire have mass? Because that was a big thing when he was around. So what he did is he took a hamster and he put it in a little ice cage like this, and that hamster had heat in it, and he knew that. And then that hamster, through its living, would start melting the ice in the ice cage, and he could capture that ice as liquid and determine how much heat was released by the hamster by knowing how much heat it takes to melt ice. And that's called the heat of fusion. So just so you know, when we do this with humans, we don't put them in a little ice cage. We surround them with water, and then that water heats up based on how much. So here's your system, the person. It heats up the surroundings, right? This water, and then you can determine how much heat got into the water, and all that heat had to come from the person. So the hamster, guinea pig, I guess, had it much worse than the person. Okay. So let's talk about this. When you heat up a solid, it gets hotter, right? You know this. If you put a pan on the stove, before you put the fire on it, you can put your hand on it. As you put fire on it, it gets hotter and hotter. It gets to a point where it starts melting, and it turns out when it's melting, the temperature will not change. We'll look at that some more. And then it turns into a liquid, and then the liquid will get hotter and hotter, right? When you boil water, it can go from room temperature to boiling. So the water gets higher and higher in temperature. And then actually when it boils, it stays the same temperature. It's 100 degrees Celsius. And then after all of it has boiled into gas, you can start heating up the gas. So this is called a heating curve. You'll be expected to know what happens at what part here. And it should make sense, right? At lower temperatures, you're solid. At mid temperatures, you're a liquid. And at high temperatures, you're a gas. These flat parts will help you know what's happening there. So here we are with the heating curve, right? You're solid, turns flat when it's melting. Your liquid turns flat when it's boiling, and your gas. All right. So during those flat parts, rather than increasing your kinetic energy, you're increasing your energy of basically separation of these things. So solid has everything packed close. Liquid has a little more movement. So you're giving them a degree of freedom, and that's where that energy goes. So you need energy to turn a liquid into a gas to give it that degree of freedom. And when gas goes back to a liquid, you take energy out. So the same energy you put in to turn liquid into a gas is the energy you get out for a gas to a liquid. So the reason a steam burn will hurt your hand is because all the energy of the gas particles to turn back to a liquid goes into your hand. And so that's why a steam burn hurts worse than putting your hand in water. All right. So there's two things, heat of fusion and heat of vaporization. Heat of fusion has to do with solid to liquid or liquid to solid. Okay. It's usually a smaller number than the heat of vaporization. Heat of vaporization is liquid to gas or gas to liquid, depending which way you go. So it's positive 2,260 for water. To turn liquid water to gas, you would release that 2,260 joules if a gas went back to a liquid. So it would be negative going backwards. And that would be endothermic going this way, right? And it's exothermic going backwards. So there'll be negative numbers. But notice how much bigger it is to make a liquid into a gas to give them that degree of freedom where they're flying around versus a solid to a liquid, because the degrees of freedom aren't that much different. So thanks to the term vaping that has swept the nation, delta H vape being a liquid to a gas makes sense to people. Fusion is a little harder to remember, fusion being solid to liquid or liquid to solid. All right, so I do expect you to know how this graph works. Okay, that you're heating up solid, melting a solid, heating up a liquid, boiling a liquid, heating up a gas. Okay, so in 1, 3, and 5, where temperatures are changing, you would use that specific heat equation. You would use delta H fusion when it's melting and delta H vaporization when it's heating to a gas. All right, so let's talk about if you had water freezing at 0 degrees, how much heat do you need to remove? It's staying at 0 degrees, so we're going to just use this equation. And delta H fusion was given as 334 joules per gram. So if it was 480 grams of water that I was trying to pull the heat out of, 480 grams times the 334 joules per gram will give me joules, and it's 160,000 joules. For heat of vaporization, that's supposed to be how sweat works. If we didn't live in North Carolina, where sweat never goes anywhere because of the humidity, you would see that sweat actually cools your body down. It does that because of heat of vaporization. So if you lost 500 grams of water, 500 mils of water, because it evaporated off your body, how much energy does that absorb? So you would use the delta H vaporization because liquid's turning to a gas. 500 times that. Look at this, 1.13 million joules of energy is released by evaporating water off your body. So that should be, impressive to you. That's cooling you off, right? That's how much heat is leaving your body if sweat actually could evaporate off your body. Now, like I said, because of all the humidity in the air, that doesn't happen. All right, so that